Hello, in this lecture we'll find out the length of line segment AE. In the drawing we have rectangle ABCD. We know that side AD equals to 3 units in its length. In addition, inside this rectangle we have those two semicircles. The radius of this big semicircle equals to 2 units in its length. The radius of this small semicircle equals to 1 unit. Again, our mission is to find out the length of this line segment AE. So first of all, we know that all the angles inside any rectangle are right angles. So those four angles, they are all right angles. So this is a right angle. This is also a right angle. This angle is a right angle. And this is also a right angle. In the next step, we will define the relevant points to this question with letters. We will define the center of this big semicircle. This point is point P. We will define the center of this small semicircle. This point is point Q. We will define the touching point of those two semicircles. This point is point S. Likewise, we will define the point of tendency of tangent AE with this big semicircle. This point is point L. And finally, we define the point of tendency of tangent AE with this small semicircle. This point is point G. In the next step, we will do a construction. That is to say, we will extend line segment AE inside the DC of this rectangle by a side line until they touch each other. Actually, this is their touching point. We will define this point as point F. So actually, we extended side DC of rectangle ABCD by a straight line. First of all, DC is one side of rectangle ABCD, and therefore it is absolutely a straight line. Then we extended the straight line DC by straight line, and the result is DF. When we extend the straight line by straight line, the result must be a straight line. Therefore DF is also a straight line. And if we focus on the upper side of this straight line DF here at point C, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the upper side of DF at point C? We have this angle that is a right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So, in the right triangle, in the right small triangle ECF, we define this angle EFC as alpha. We continue to focus on the right small triangle ECF. In the right small triangle ECF, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the right triangle ADF, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. according to the sum rule that said that the sum of the angles in any triangle is equal to 180 degrees. So here we have line segment PD equals to PS, both the radii of this big semicircle is equals to 2, therefore each of these line segments will be equal to 2 units. So PD equals to 2 and PS also equals to 2. Likewise, QS equals to QC, both the radii of this small semicircle is equals to 1. So QS equals to 1 and QC also equals to 1. Here we have line segment CF. We will define the length of this line segment CF as x. So here we have the radius PL of this big semicircle is drawn to point L, that is the point of tendency of tangent AE with this big semicircle. And whenever you have a radius that is drawn to the point of tendency, you can implement rule 1. And since we can rule 1, according to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have a circle, and we have also here tangent AB, that is tangent to this circle at point M. In addition, we have the radius OM. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to this rule, rule 1. So we can implement rule 1 in our drawing. Why? Because in our drawing we have the radius PL of this big semicircle that is drawn to point L, that is the point of tendency of tangent AE with this big semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AE will be perpendicular to the radius LP. If AE is perpendicular to LP, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. Likewise, we have the radius QG that is drawn to point G, that is the point of tendency of tangent AE with this small semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AE will be perpendicular to the radius GQ. If A is perpendicular to GQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the sum rule, rule 1. So in the small right triangle GQF, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. According to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. Likewise, in the big right triangle LPF, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. So write it down, this angle equals to 90 degrees minus alpha. In the next step, we prove that the big right triangle LPF is similar to this small right triangle GQF. So write it down. So we prove that the big right triangle LPF is similar to this small right triangle GQF. So why those two right triangles are similar to each other? First of all, those two angles, they are both equal to 90 degrees and therefore they are equal to each other. So actually this is angle PLF. in the big right triangle LFP, and it is equals to this angle. That's actually angle QGF. In the small right triangle GFQ. So repeat again. Let us find out that angle PLF in the big right triangle LFP equals to angle QGF in the small right triangle GQF. They're both equal to 90 degrees, and therefore they are equal to each other. In addition, this is angle alpha. This is a common angle that belongs to both triangles. So we can write down that angle alpha equals to itself is a common angle that belongs to both triangles. So if we relate to this angle, angle alpha, as it belongs to the big right triangle LFP, it will be defined as angle LFP. And angle alpha equals to itself. So if we relate to this angle, angle alpha, as it belongs to the small right triangle ECF, into the small right triangle GQF, it will be defined as angle GFQ. So repeat again. This equation means that angle alpha equals to itself. We just call to angle alpha two different names. Angle alpha equals to itself is a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually, this is angle LPF. In the big right triangle LFP, and it is equal to this angle, that is actually angle GQF. In the small right triangle GFQ. So repeat again, we actually found out that angle LPF in the big right triangle LPF equals to angle GQF in the small right triangle GFQ. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we actually found out that all the figures in this big right triangle LPF are correspondingly equal to all the figures in this small right triangle GQF, and therefore those two right triangles are similar to each other according to angle similarity rule. So write it down. We actually found out that the big right triangle LPF is similar, this is the sign of similar, to the small right triangle GQF according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side LP in the big right triangle LPF over side GQ in the small right triangle GFQ equals to side PF in the big right triangle LFP over side QF in the small right triangle GFQ. So I'll put it again. So we can derive that side LP in the big triangle over side GQ in the small triangle equals to side PF in the big triangle over side QF on the small triangle. LP is the radius of this big semicircle that is equal to 2 over GQ. GQ is the radius of this small semicircle that is equal to 1, and is equals to PF. PF in total equals to 2 plus 1 plus 1, that is 4 plus x. So PF in total equals to 4 plus x. Over QF. QF in total equals to 1 plus x. So in conclusion, we found out that 2 equals to 4 plus x over 1 plus x. Here we multiply this equation by 1 plus x. And we get that 2 times 1 plus x equals to 4 plus x. So here we'll open the brackets on this side of the equation and we get that 2 times 1 is 2 plus 2x equals to 4 plus x. So here we subtract x from this equation and we get that 2x minus x is x. So in total in this side of the equation we have x plus 2 equals to 4. Here we subtract 2 from this equation and finally get that x equals to 4 minus 2, that is 2. So we actually found out that the length of this line segment CF is equals to x is equals to 2 units. So I'll write it down. In the next step, we prove that the big right triangle ADF is similar to this small right triangle ECF. So I'll write it down. We prove that the big right triangle ADF is similar to this small right triangle ECF. So why the big right triangle ADF is similar to this small right triangle ECF? First of all, those two angles are both equal to 90 degrees and therefore they are equal to each other. So actually this is angle ADF. In the big right triangle AFD, and it is equals to this angle, that is actually angle ECF. In the small right triangle EFC. So I'll repeat again. Actually found out that angle ADF in the big right triangle ADF equals to angle ECF in the small right triangle ECF. They are both equal to 90 degrees and therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both angles. So I can write down that angle alpha equals to itself as a common angle that belongs to both angles. So if we relate to this angle, angle alpha, as it belongs to the big right triangle ADF, it will be defined as angle AFD. And angle alpha equals to itself, so if we relate to angle alpha as it belongs to the small right triangle ECF, it will be defined as angle EFC. Again, this equation means that angle alpha equals to itself. We just call to angle alpha two different names. Angle alpha equals to itself as a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually this is angle DAF in the big right triangle AFD, and it is equal to this angle. This is actually angle CEF in the small right triangle EFC. So repeat again, we shall find out that angle DAF in the big right triangle AFD equals to angle CEF in the small right triangle EFC. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we actually proved that all the three angles inside the big right triangle ADF are correspondingly equal to all the three angles in this small right triangle ECF, and therefore those two right triangles are similar to each other according to angle similarity rule. And from the fact that the big right triangle ADF is similar to this small right triangle ECF, we will derive that the following relationship exists between their sides. We will derive that side AD in the big right triangle ADF over side EC in the small right triangle ECF equals to side DF in the big right triangle AFD over side CF in the small right triangle EFC. I'll repeat again. We will derive that side AD in the big triangle over side EC in the small triangle equals to side DF in the big triangle over side CF in the small triangle. AD equals to 3 over EC. EC is the missing side, so we will leave it as it is. And it is equals to DF. DF in total equals to 2 plus 2 plus 1 plus 1, that is in total 6 plus 2. 6 plus 2 is 8. So in total DF equals to 8 over CF. CF equals to 2. So in total we have found out that 3 over EC equals to 8 over 2. 8 over 2 is 4. So I write it down. So we have found out that 3 over EC equals to 4. Here we multiply this equation by EC, and you get that 3 equals to 4 times EC. So here we divide this equation by 4, and finally get that the missing side EC equals to either 3 quarters or 0.75 units. So actually this is the missing side EC. This equals to either 3 quarters or 0.75 units. So I write it down. EC equals to 0.75 units. What is the length of side BC of rectangle ABCD? You know that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AD equals to the opposite side BC. But AD is 3, therefore BC must be also equal to 3. So I write it down. So I shall found out that BC equals to 3 units in its length. What is the length of side BE? From the drawing it is very easy to see that BE equals to BC minus EC. Again, BC minus EC equals to BE. So I write it down. BE equals to BC minus EC. So BE in total equals to BC, that is 3, minus EC, it is 0.75. So BE equals to 3 minus 0.75 is 2.25. So this is nice segment BE, that is equals to 2.25 units in its length. What is the length of side AB of rectangle ABCD? According to the same rule, that the opposite sides of a rectangle are equal to each other, we will get that in rectangle ABCD, side AB must be equal to the opposite side DC. But DC equals to 2 plus 2, that is 4, plus 1, that is 2, and 4 plus 2 is 6. So in total DC equals to 6 units, and therefore the opposite side AB must be also equal to 6 units. So AB equals to 6 units. In the next step, I'll copy the right green triangle ABE in a new page, and we'll implement the Pythagoras theorem in this right green triangle ABE. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is a relation for Pythagoras theorem. Side AB equals to 6 units in its length. Side BE equals to 2.25 units. And the hypotenuse AE is the missing side. So actually, this is the green right triangle ABE that they covered from the original drawing. According to the Pythagoras theorem, in this right triangle ABE, AE squared, that is the square of the hypotenuse, equals to AB squared plus BE squared. So I write it now. So AE squared equals to AB squared plus BE squared. AE is the missing side, so we will leave it as it is. AE squared equals to AB squared. AB is 6, therefore AB squared is 6 squared, that is 36, plus BE squared. BE is 2.25, therefore BE squared is 2.25 squared, that is actually 5.0625. So in total we found out that AE squared equals to 36 plus 5.0625. 36 plus 5.0625 equals to 41.0625. So we found out that AE squared equals to 41.0625. So here we take a root out of this equation and finally we get that the missing line segment AE, that is also the hypotenuse of this right triangle ABE, is equals to the square root of 41.0625, that is actually equals to 4.60, it is equals actually to 6.408 units. And that is the answer to the question. So I repeat again, I found out that the length of this line segment AE is equals to 6.408 units. So in the next step, I will summarize the lecture. In this lecture, we found out the length of this line segment AE. So in the drawing, we have rectangle ABCD. We know that side AD equals to 3 units in its length. In addition, inside this rectangle, we have those two semicircles. The radius of this big semicircle equals to 2 units in its length. The radius of this small semicircle equals to 1 unit. Again, our mission is to find out the length of this line segment AE. So first of all, we know that all the angles inside any rectangle are right angles. So those 4 angles, they are all right angles. In the next step, we define the relevant points to this question with letters. We define the center of this big semicircle, this point as point P. We define the center of this small semicircle, this point as point Q. We define the touching point of those two semicircles, this point as point S. Likewise, we define the point of tendency of tangent AE with this big semicircle, this point as point L. We define the point of tendency of tangent AE with this small semicircle, this point as point G. In the next step, we did the construction. That is to say, we extended side AE or line segment AE and side DC of this rectangle ABCD by a straight line until they touch each other. They touch each other in this point F. We define their touching point as point F. So we know that DC is one side of rectangle ABCD and therefore it is absolutely a straight line. By doing the construction, we extended side DC by straight line and the result is DF. So when you extend the straight line by straight line, the result must be a straight line. So and therefore DF must be a straight line, because this is a straight line. Okay, and then we focus on the upper side of the straight line DF at point C. And the upper side of DF at point C, here the sum of the angles must be equal to 180 degrees according to rule 3 that states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of DF at point C? We have this angle that is the right angle plus this missing angle. In total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. Okay, so in the right triangle ECF, in the small right triangle ECF, we define this angle EFC as alpha. So in the right small triangle ECF, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the big right triangle in DF, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha according to the sum rule that states that the sum of the angles in any triangle is equal to 180 degrees. Here we have PD equals to PS. They are both the radii of this big semicircle equal to 2, therefore each of these 9 segments must be equal to 2. Likewise, we have here QS equals to QC. Each of these 9 segments must be equal to 1 because both of them are the radii of this small semicircle that's equal to 1. Here we define the length of this 9 segment CF as X. So here we have the radius PL of this big semicircle that is drawn to point L, that is the point of tendency of tangent AE with this big semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AE will be perpendicular to the radius LP. If A is perpendicular to LP, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. Likewise, we have the radius QG of this small semicircle is drawn to point G, that is the point of tendency of tangent AE with this small semicircle. And whenever your radius that is drawn to the point of tendency, then tangent AE will be perpendicular to the radius GQ. If A is perpendicular to GQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. So inside the small right triangle GQF, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha, according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. Likewise, in the big right triangle LPF, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. In the next step, we proved that the big right triangle LPF is similar to this small right triangle GQF. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees and therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles. So we can write down that angle alpha equals to itself as a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we actually proved that all the angles inside the big right triangle LPF are correspondingly equal to all the angles inside the small right triangle GQF, and therefore those two right triangles are similar to each other according to angle similarity rule. So if it again, I shall find out that the big right triangle LPF is similar to the small right triangle GQF according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side LP of the big right triangle LPF or side GQ of the small right triangle GFQ is equals to side PF of the big right triangle LPF over side QF of the small right triangle GFQ. So repeating again, we will derive that side LP of the big triangle or side GQ of the small triangle equals to side PF of the big triangle or side QF of the small triangle. LP is the radius of this big semicircle, that is 2. GQ is the radius of this small semicircle, that is 1. And it is equals to PF. PF in total equals to 2 plus 1 plus 1, that is 4 plus x. So PF in total equals to 4 plus x over QF. QF in total equals to 1 plus x. So we can find out that 2 over 1 equals to 4 plus x over 1 plus x. Here we multiply this equation by 1 plus x, and finally found out that 2 times 1 plus x equals to 4 plus x. Here we open the brackets on this side of the equation and found out actually that 2 times 1 is 2. So in total on this side of the equation we have 2 plus 2x equals to 4 plus x. Here we subtracted x from this equation and finally found out that 2x minus x is x. So in total in this side of the equation we have x plus 2 equals to 4. Here we subtracted 2 from this equation and finally found out that x equals to 4 minus 2, that is 2. So we found out that the missing 97 CF, that is equals to x, according to our definition, is equals to 2 units. In the next step, we proved that the big right triangle ADF is similar to this small right triangle ECF. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees and therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles. So we can write down that angle alpha equals to itself as a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So I should have proved that all the angles inside the big right triangle ADF are correspondingly equal to all the angles inside the small right triangle ECF. And therefore those two right triangles are similar to each other according to angle similarity rule. So if it again, I should have found out that the big right triangle ADF is similar to the small right triangle ECF according to angle similarity rule. And from the fact that the big right triangle ADF is similar to the small right triangle ECF, we derive that the following relationship exists between their sides. We derive the side AD in the big triangle or side EC in the small triangle equals to side DF in the big triangle or side CF in the small triangle. Repeat again. We derive that side AD in the big right triangle ADF or side EC in the small right triangle ECF equals to side DF in the big right triangle ADF over side CF, the small right triangle ECF. AD is 3 over CE. CE is the missing side, so we leave it as it is. Equals to DF. DF in total equals to 2 plus 2 plus 1, that is in total 6, plus 2. 6 plus 2 is 8. So in total DF equals to 8 over CF. CF is 2. So if I found out that in conclusion that 3 over EC equals to 8 over 2. 8 over 2 is 4, so in total we found out that 3 over EC equals to 4. Here we multiply this equation by EC, and finally found out that 3 equals to 4 times EC. Here we divided this equation by 4, and finally found out that the missing side EC equals to either 3/4 or 0.75 units. So this is the missing side EC, that is equals to either 3/4 or 0.75 units. What is the length of the missing side BC of rectangle ABCD? We use the rule that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AD must be equal to the opposite side BC, but AD is 3, therefore BC must be also equal to 3 units instead. BC is 3. So what is the length of the missing line segment BE? BE equals to BC minus CC. Again, BE equals to BC minus CC. BE equals to BC minus CC. B equals to BC minus CC. So B equals to BC, that is 3, minus EC, that is 0.75. So in total, BE equals to 3 minus 0.75, that is 2.25. Okay, again, BE equals to 2.25 units in its length. According to the same rule that the opposite sides of a rectangle are equal to each other, we get that in rectangle ABCD, side AB must be equal to the opposite side DC. But DC equals to 2 plus 2, that is 4, plus 1 plus 1, that is 2, and 4 plus 2 is 6. So DC in total equals to 6, and therefore the opposite side AB must be also equal to 6. In the next step, I copied the green right triangle ABE in a new page and implemented the Pythagoras theorem in this green right triangle, triangle ABE. So actually, this is the green triangle ABE that I copied from the original drawing. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in this right triangle ABE is AE. Therefore, the square of the hypotenuse is AE square, and it must be equal to AB square plus BE square. Again, AE square equals to AB square plus BE square. AE is the missing side, so we limit as it is. So AE square equals to AB square. AB is 6, therefore AB square is 6 squared, that is 36, plus BE square. BE is 2.25, therefore BE square is 2.25 squared, that is 5.0625. So in total, AE square equals to 36 plus 5.0625. 36 plus 5.0625 equals to 41.0625. So in total, we found out that AE square equals to 41.0625. Here we took a root out of this equation and finally found out that the missing 970 AE equals to the square root of 41.0625. That is actually equals to 6.408. So in conclusion, we found out that the envelope of this 970 AE equals to 6.408 units. Okay, thank you very much.